We're going to look at hypothesis tests of the population mean when the population standard deviation is unknown. And we're going to be looking specifically at two-tailed tests. Two-tailed tests are hypothesis tests that look like this. The null hypothesis is that the population mean is equal to some value, mu naught, and the alternative hypothesis is that the population mean is not equal to that value. So the example of a two-tailed test that we're going to look at is mu naught is equal to 18. The sample size is equal to 48. The sample mean is equal to 17. The sample standard deviation is equal to 4.75. And the level of significance, alpha, is equal to 0.05. So the first step in a hypothesis test is always to calculate the test statistic. Now, since sigma is unknown, we're going to write our test statistic as t, and it's going to be equal to x bar minus mu naught over s divided by the square root of n. Now our test statistic is written t here because it follows a t distribution and a t distribution has a degrees of freedom associated with it. The degrees of freedom here is going to be n minus 1. So let's start our example by calculating the test statistic. So we have t is equal to 17 minus 18 over 4.75 divided by the square root of 48, which is equal to negative 1.46. So our test statistic is negative 1.46. Now there are two different ways that we can use our test statistic. The first way is with the p-value approach. In the p-value approach, we calculate a p-value, and for a two-tailed test, the p-value is the probability of getting a value for the test statistic as unlikely as or more unlikely than the value that's computed from the sample. So let's take a look at what this definition is saying. So when it says the probability of getting a value for the test statistic, It's talking about a t-value because our test statistic follows a t-distribution. So it's the probability of getting a t-value as unlikely as or more unlikely than the value from the sample. Now the value from the sample is whatever we calculate for our test statistic. In our example, we calculated the test statistic to be negative 1.46. Now what makes this the definition of a two-tailed test is this part here, as unlikely as or more unlikely. Now, if it was a lower tail test or upper tail test, the definition would be exactly the same except for this underlined part. If it was a lower tail test, the underlined part would say as small as or smaller, and if it was an upper tail test, it would say as large as or larger. So let's calculate the p-value here. So our test statistic from the sample is negative 1.46, and our test statistic follows a t-distribution with n minus 1 degrees of freedom. So this t-distribution has a degrees of freedom equal to 48 minus 1, which is equal to 47. So our test statistic is negative 1.46. So we want to find the values of t that are as unlikely as or more unlikely than negative 1.46. So we just want to look at where the height of the curve is lower than where it is at negative 1.46. So it's going to be all the values of t that are less than negative 1.46, but they're also going to be the values of t that are greater than positive 1.46. Because the t distribution, like the z distribution, is symmetric. So the left side is equal to the right side. So to get our p-value, we want to take both of these areas, the area to the left of negative 1.46 and the area to the right of positive 1.46. Now, these areas are actually going to be equal, again, since the t-distribution is symmetric. So instead of finding the two areas separately, what we can do is find one of the areas and then double it. Now, since our t-table gives us the area to the right, it will be easier to find the area to the right of positive 1.46 than to find the area to the left of negative 1.46. So to get our p-value, what we'll do is we will double the area to the right of positive 1.46. So let's take a look at our t-table. We want to look for 1.46 and 47 degrees of freedom. So this is the first page of our t-table. It starts from a degrees of freedom of 1 and goes up to 34. So we're going to be on the next page. 47 degrees of freedom is here. And our t-value is 1.46. So 1.46 is going to fall between 1.3 and 1.678. So you see, we don't have the exact area here. We know that 1.3, see that 1.3 gives an area of 0.1, and we see that 1.678 gives an area of 0.05. Our t-value is between these two t-values. Our t-value is 1.46. So it falls between 1.3 and 1.678. So our p-value falls somewhere between here. So we don't know the exact p-value. What we have is a range for our p-value. So our p-value is going to be 2 times 0.05 to 0.1, which is going to be 0.1 to, so we just double each number, we get 0.1 to 0.2. Now that's the most information that we can get from our t-table, and it's enough to solve this problem. But if we want to get the exact value, we can use a computer program like Excel or R, and we can calculate the exact p-value. And if you do that, you'll see that the exact p-value is 0.1513. So you see 0.1513 is between 0.1 and 0.2. But we can't get this exact p-value from our table because our table is limited. So we can get from our table that it's between 0.1 to 0.2. Again, this is enough to solve this problem. So the next step is to use the rejection rule for the p-value approach, which says to reject the null if the p-value is less than or equal to the level of significance. Now, this is the rejection rule of the p-value approach for any hypothesis test, meaning that whether it's lower tail, upper tail, two-tail, if sigma is known, if sigma is unknown. So there's a total of 6 different combinations for hypothesis testing, and all 6 versions, they all have the same exact rejection rule for the p-value approach. Reject the null if the p-value is less than or equal to alpha. So you can see that our p-value is 0.1 to 0.2. So our p-value is greater than our alpha of 0.05. So our conclusion is to not reject the null. So we would reject the null. We would reject the null if the p-value was less than or equal to alpha, but since it's greater than alpha, we do not reject the null. That's our conclusion. So the second way of using the test statistic is with the critical value approach. Now, in the critical value approach, we're going to calculate actually 2 critical values here. Since it's a two-tailed test, there's going to be 2 critical values. If it's a one-tailed test, either a lower tail or upper tail, then there's only going to be 1 critical value. But in a two-tailed test, there's 2 critical values. And our 2 critical values are going to be negative t alpha half and positive t alpha half. Negative t alpha half is going to be the value of the test statistic. Now, when we say value of the test statistic, we're essentially saying the t-value because the test statistic follows a t-distribution. So value of the test statistic corresponding to an area of alpha half in the lower tail. Okay, so note that we said lower tail here, and that's because it's negative t alpha half. So positive T alpha half is going to be the same thing we're writing here, except it's going to say upper tail. Also note that we split our level of significance alpha in two, and we gave half of alpha to each of the critical values. When we're doing a lower tail test, we have one critical value and it gets all of the alpha. But since we have two critical values, we give half an alpha to each. So it's the value of the test statistic corresponding to an area of alpha half in the lower tail of the sampling distribution of the test statistic. Now, sampling distribution of the test statistic is just a fancy way of saying the t-distribution with n-1 degrees of freedom, because that's what the sampling distribution of our test statistic is going to be here when sigma is unknown. So our positive T alpha half is going to be the same exact thing except it's going to say upper tail. Instead of in the lower tail, it's going to be the T value in the upper tail. So let's simplify this definition here. What it's saying is it's the T value with an area of alpha half in the upper tail of the T distribution with n-1 degrees of freedom. Okay, so those are our two critical values, so let's find them. It's always helpful to draw the graph. It prevents you from making mistakes. So let's see, the degrees of freedom is n-1, and n is 48. So 48 minus 1 is equal to 47. Now we have two critical values. We have negative T alpha half, and we have positive T alpha half. So these are going to be the T values that give areas of alpha half. Now our alpha is 0.05, so alpha half is 0.025. Okay, so since the T distribution is symmetric, all we have to do is find one of these, and the other one is going to be the negative of it. Now, since the t-table gives us the area to the right, we want to find the positive critical value, T alpha half. So let's look for the T value that gives an area of 0.025 under a T distribution with 47 degrees of freedom. Okay, so we want to match up 47 degrees of freedom with an area in the upper tail of 0.025. Okay, so 47 degrees of freedom, matching it up with 0.025, we get 2.012. So T alpha half is positive 2.012, which means that negative T alpha half is just going to be the negative of that, negative 2.012. So those are critical values, negative 2.012 and positive 2.012. Now, our rejection rule for the critical value approach is to reject the null if our test statistic t is less than or equal to negative t alpha half, or if our test statistic t is greater than or equal to positive t alpha half. So if our test statistic is less than or equal to the negative critical value or greater than or equal to the positive critical value, we reject the null. Now, if it's between the two critical values, then we do not reject the null. So in other words, if our test statistic is in this region here that's not shaded, we do not reject the null. If it's in either of the shaded regions, then we reject the null. Now our test statistic is between 0.1, our test statistic is negative 1.46. Now negative 1.46 so it's greater than our negative critical value, and it's less than the positive critical value. So neither of the conditions of the rejection rule are satisfied. Neither of these conditions. So only one of these conditions need to be satisfied. Either the test statistic has to be less than or equal to negative t alpha half, or it has to be greater than or equal to positive t alpha half. Neither of those conditions are satisfied because it's greater than negative t alpha half and it's less than positive t alpha half. So we can't reject the null. The conclusion again is do not reject the null. Which is the same conclusion that we came to with the p-value approach.